So, good afternoon, ladies and gentlemen, and welcome to this plenary session. Thank you for being here. It's my honor to introduce Emig Thorsten for this session at the heart of the questions of this edition of ACAPS, contribution of technologies and digital in physical and sports activities at the crossroads of digital, artificial intelligence, and sports performance. Indeed, with Emig, we will address the issue taking the lab to the real world. What can we learn from big data in endurance sports? But at first, let me briefly introduce Emig. Emig received his PhD degree in theoretical physics from the University of Cologne in 1998. In 1999, Emig came to the French Atomic Commission in Saclay as a postdoctoral researcher to work with the French physician Jean-Philippe Bouchot. Later, he joined the group of Professor Mehran Parda at MIT in Cambridge to work on problems in statistical physics. In 2001, he established a junior research group at the University of Cologne, where he developed novel approaches to study the forces induced by fluctuations at the nanoscale. This work at the intersection of statistical physics, scattering theory, and classical electromagnetism has revolutionized the conceptual framework in which fluctuation forces are considered. In 2006, Emig joined CNRS at the Laboratoire de Physique Théorique et Modèle Statistique at the University Paris Sud. Emig has spent sabbatical years at University Cologne and MIT as a Heisenberg Fellow. From 2014 to 2018, he was appointed as senior research scientist at the MIT CNRS International Joint Laboratory at MIT, where he started a number of new interdisciplinary research activities, including climate physics and sports science. His research in sports science builds on the rapidly growing amount of available exercise data from wearable devices, which hold a great potential for new quantitative research. While traditional lab studies are limited to by a small sample of participants, big data collections make it possible to bring the laboratory to the road and study millions of subjects under real-world conditions. In his recent project, Emig has developed a universal theoretical model for endurance performance and applied it to exercise data from thousands of runners, predicting marathon race times accurately and identify key predictive parameters of running performance. He has also used methods from statistical physics to analyze fluctuation of the human heartbeat during physical exercise. So Emig, I turn it over to you for your 35 to 40-minute presentation.
Bonjour. Thank you very much for this nice introduction. It's a pleasure to be at this interesting conference in beautiful Montpellier. And I guess it doesn't happen too often that a theoretical physicist is invited to a sports conference. So during the last days, I've seen really interesting talks by data scientists and experts on complex systems. And this altogether makes me believe that sports science seems to start to become a really interdisciplinary field of research. And I think that this really holds great potential for the future. So today, I would like to convince you that the data that are collected by connected devices like running watches can be used to extract some useful information on physiological parameters and then study the relation between these parameters and sports performance, running performance, and also relation to training and how to guide training. So let us start by looking at one of the largest internet platforms where runners can upload, and runners and cyclists can upload their physical activity data. Its name is Strava, you probably have heard about it. And this web service last year had about 73 million users who completed more than 1 billion activities just last year. And if you look just at the runners that use this service, we see that there have been about 2 billion miles recorded just last year by the runners that use this service. And what I found interesting is that the pandemic has actually increased the number of data that are collected, presumably due to the fact that gyms and indoor facilities were closed and people started to do physical activity outdoors. And so this is reflected by this big increase in the amount of data, which at the peak were about 30 million activities per week uploaded to this service. So having all this data, one might wonder what information is encoded in all this exercise data. And it's certainly a complex adaptive system, the interplay between training and performance. And so there are two questions related to such a complex system. The first is, can we understand various aspects of the system, and can we predict things like performance or how performance is changed by certain modes of training? And what might be interesting is that sometimes you can make predictions without understanding every single component of a system. Think about the forecasting of weather conditions, right? We don't need to understand at the microscopic details how all molecules in the atmosphere move, but instead there are some macroscopic models that do a quite good job in predicting things. So there are different levels of understanding, and you could ask, can we understand the biological process on the level of genetics or the cell? But you could also ask, is there a more macroscopic approach to make at least some predictions and understand basic factors that determine performance as a function of training. And today I would like to show you one such simple model that allows us to do this and extract information from big data. So the questions that I would like to address are, can these data that are collected by these watches replace or at least complement laboratory tests of athletes? Can we follow over time the evolution of these parameters as they change with training? And can we find a more efficient way to guide training? So I mentioned already that there are some simple models, of course, on the market that can describe athletic performance, and I'm talking today only about running, so running performance. And so these models are often based on a single parameter. And one parameter that is commonly used is the so-called maximum oxygen uptake, VO2 max. And these variables are usually fixed at some typical parameters. But physiological profiles and parameters are, of course, individually different. And one good example from running is that the energy cost of running can be very different. For example, if you look at a runner and ask him to run at a speed of about 16 kilometers per hour, that's about 3 minutes 45 seconds per kilometer, and you measure the oxygen required to run at this speed, you measure values between about 41 up to 67 milliliters per kilogram a minute. So there's a huge variability in what we call the running efficiency. So a model that fixes this parameter is deemed to fail. Also, these parameters, of course, adapt to training. That's the goal. And so we can't fix these parameters in a model that is supposed to describe training response. Another problem is that not all of these quantities can be measured easily in the lab. For example, if you would like to study the long time endurance of a runner, you had to ask the runner to run 2, 3, or even 4 hours inside the lab. And you can easily imagine that this is... I didn't do anything? Okay. You can imagine that this is not very realistic. It's really artificial setting, and the measurement is probably not very realistic. So therefore, it would be interesting to use this data from smart devices because they collect the data in the real world, outside the laboratory. And of course, these devices have not the same, let's say, precision than lab equipment, but they have another advantage. They can monitor athletes in the real world, under real world conditions, for a long period of time. So, here I would like to show you what the current industry standard, let's say, is in these smart watches or running watches. So they already contain some algorithm that allow you to estimate basically one parameter, which is the maximum oxygen uptake. But these watches do it slightly differently, so they measure your heart rate, and then from the relation between heart rate and your running speed, they try to estimate the oxygen uptake. And in this scatter plot here, I show you data from runners that have completed a marathon. This is the time they achieved, and this is the estimate for what is believed to be VO2 max done by these watches. And so these are about 38,000 marathon runs. And as you can see, the data have a wide range of scattering. So if you look, for example, at VO2 max estimate of 60, you find times between, let's say, 3 and 5 hours or even beyond. So this parameter is not very useful in reality, as you can see. Or if you ask, what index do I need on this watch to run a marathon below 3 hours, it can be anywhere between 60 and 80. So something is missing here. The model seems to be too simple, or the estimates are not accurate. Probably both is the case. So we have to find a better description of running performance. So before I describe our model, I would like to quickly go over some of what I think are the key concepts. You know this probably much better than me as a physicist, but anyway, I would like to just for completeness go over this concept. So the first concept is the concept of running economy. So this is the metabolic energy required to run at a given speed. It's measured in terms of the oxygen consumption per body weight and time. And to a very good approximation, it's a linear relation. This is true for running, not for cycling, because running speeds are so low that you can ignore air resistance or any drag forces. So therefore, it's to a good approximation a linear relation. But what I mentioned before already, this linear relation can be quite different for different runners. And I'm showing you 3 different runners that have a personal best time on 3,000 meters that is almost identical. So, but their running economy is very different. So how can it be that they all run more or less the same time over 3,000 meters? Well, what is important is actually not the absolute value of the maximum oxygen uptake, but the speed that corresponds to this maximum oxygen uptake. So you could say less economical runners need more oxygen, but they maybe also have a higher maximum oxygen uptake to compensate for that. So what therefore is an important parameter is the speed at VO2 max, the running speed at VO2 max. The second important concept is endurance, and that's a little bit more complicated. So when we looked at the literature, we found a lot of ad hoc proposals for what this could be. And so I should tell you what I mean by endurance. Endurance is not a priori not a single parameter, it's a function. And it's a function that tells you what power output relative to the maximum power output a runner can maintain over a given time. So it's a function, power as a function of time. And of course, if time becomes longer, the power has to go down. Okay? So we are looking for this function. And there has been a proposal made about 100 years ago by the famous physiologist Hill, known as the running curve, and the ansatz is quite simple. He said there's anaerobic energy AN that's available. It's a fixed amount of energy that is available over the time t. So energy, power is energy divided by time, so this is the first contribution. And then there is aerobic energy which is renewable over time, so therefore this is a constant. So this is a proposal for the power output as a function of time. But you can easily see that if time becomes very long, the first term tends to 0 and the power output tends to a constant. But for very, very long times this can't be true, because this would mean that you can run, let's say, a marathon at the same speed than a 10,000 meter race. And this is clearly in contradiction to real-world observations. So this is can be only valid up to a certain time scale. So we were wondering what this function could look like. But what we found very interesting is that Hill himself made a very important observation 100 years ago when he plotted various athletic records like cycling, skating, and also running, and this here is for running, on the following graph. He plotted the average speed of the event as a function of the logarithm of the duration. So this is a logarithmic scale. And if he does this, he found a linear relation between the average speed and the logarithm of the duration. It's linear here, and then there's another linear branch here. And so what we found is that our model, when we solve it, actually predicts two perfectly straight lines that merge at a certain time scale, which is about 6 minutes. And this seemed to match qualitatively the observation that Hill made already a long time ago. So this was something we said, okay, maybe you're on the right track. And I don't want to go into the mathematical details of the model. I just want to show you the basic concept and then focus on the results and the practical applications. So this model is just based on power, aerobic and anaerobic power. It's universal in the sense that it doesn't contain any fixed parameter. All parameters in the model will be determined from actual performance data, or the big data that we recorded with these devices. And one basic idea in this model, which is required to make this prediction for the function that describes endurance, is that we build on the experimental observation that has been made that the power to run at a given speed actually increases with the duration of exercise. So what I told you in the beginning, that running economy is a linear relation, well, that's true, but the slope of this relation can change over time. So if you measure this energy cost of running in the lab, it's usually done for 5, 10, 15 minutes, but not for 2 or 3 hours. And so this is going to change. And we incorporated this observation in our model, solved the model, and found this relation that Hill had observed experimentally. Now, what are the parameters in our model? We try to really keep it simple, because as a physicist, you try to find a model that is sufficiently simple and contains only as many parameters as they are needed to explain experimental observation. Otherwise, you're at risk if you have too many parameters that you can basically fit any experimental observation. Okay, so the first parameter is a combination of the maximum power output, VO2 max, and the running economy. And if you combine both, as I showed you before, the important quantity is a maximal aerobic speed, or in French it's VMA. And the third component is the endurance. And to parameterize our endurance function that we got from solving the model, we need 3 parameters. The first one is the time to exhaustion at VO2 max. So this is the time over which maximum aerobic power output can be maintained. And then there are 2 more parameters that we call the indices of endurance that describe how the power output changes if we move away from maximum aerobic power output, either to the aerobic side, so power output goes down, or to the anaerobic side, where the power output can be actually higher than the maximum aerobic power output. Okay, so these are the 2 parameters of endurance. And the variable in our model is not the power itself, but it's a rescaled power to make it applicable to all runners without knowing the actual maximum power scale. This is a common concept in physics, that you rescale quantities to make them dimensionless, and so that you can construct universal relations. And this is what we have done here. So we measure the power, the relative power P, as the ratio of the actual power minus the basal power, that's the basal metabolic power at rest, and divide by the difference between maximum power and basal power. Okay. So therefore, in the aerobic range, this parameter varies between 0 at rest and 1 at VO2 max, but it can be also larger than 1 for a short period of time due to anaerobic energy contributions. Okay. Now, this is a snapshot of what the endurance function looks like. So I'm showing here the time t over which a relative power output P, which varies between 0 and 1 in the aerobic range and is larger than 1 in the aerobic range, can be maintained. So as you can see, this is a curve that changes exponentially. The time changes exponentially with this relative power. And there are 2 parameters in the aerobic and anaerobic range, which are called gamma. And these parameters can be used to define endurance indices. A long-term or aerobic endurance index, which is basically the index that, if it's multiplied with the time to exhaustion at VO2 max, gives the duration over which 90% of maximum power can be maintained. And similarly, on the anaerobic side, I define an endurance that measures the time over which 110% of maximum aerobic power can be maintained. So this might sound a little theoretical, but if we combine this function now with the running economy, the linear relation, we can actually estimate running performances, or if we know the running performances, can estimate the physiological parameters of our model. And how this works, I would like to show you first for the current running world records before I come to the big data. So we first would like to see how the model works. And so we looked at the running world records for man and woman for distances between 3,000 meters and the marathon distance. This is distance in rescaled units. It's on a logarithmic scale again, so that this becomes linear. And this is the average velocity. The data points are the current world records, and the straight line is our model. We observed an average error between the model predictions and the actual times of only 0.12% for men and about 0.57% for women. So this seems to really work nicely in the anaerobic and aerobic range. We could estimate the time scale at which you have this crossover between mainly anaerobic or mainly aerobic energy contributions. But you also see that there are, for the woman, two data points, that's the 1500 meters and the 3000 meters, that seem to deviate from our model. Not much, but more than the other distances. And so we looked at this, the 3000 meter race, which has an error of more than 1%. It's not much, but it's much more than the other distances. And we found that this is actually an old result. It's a current world record on 3000 meters, dating back to 1993. And now there's strong belief that this result was obtained under the influence of drugs. And the other case is a 1500 meter result, which now is also believed to be influenced by performance-enhancing substances. So we could see this already from our model, that there's something wrong with these times. And what we have heard, it seems to be indeed the case. So these are the current world records. What I would like to show you, this is unpublished, so we just did this recently. We decided to go back over the last 100 years to look at running world records. And this is now the main running world records. And for each year, estimate the physiological parameters to see how they change. And I'm showing you here the maximum aerobic speed in meters per minute over the years. And you can see there's almost linear increase with some fluctuations, of course, but then there's a sudden jump in the 1990s. And then again a plateau or even a downward trend. And what we believe is that this is actually the area due to the era of eprodoping. So there you can see this big jump in the maximal aerobic speed in the running world records. And then there were, of course, tests introduced to detect this type of doping, and this is probably why this increase stopped, and there's even a downward trend. On the right panel, I show you the endurance index as a function of the years, 100 years. It is almost constant until the 1950s, and then there's a strong increase, which is most likely linked to a different mode of training. Runners started to do really run longer distances. Things changed a lot, the training changed a lot in the 50s and 60s. So this explains probably this big increase in endurance. Then there are some modulations, and we think that this is actually a very interesting increase since 2000, linear increase, that this is due to the occurrence of African marathon runners in the big marathon races, and that this is linked to the substantial increase of endurance reflected by the world records. Then there was a plateau until a few years ago, and then a sudden jump. And so we were wondering what this jump is, and if you look really at the times, they basically start to increase exactly at the time when new running shoe technology was introduced. So they use now carbon fiber plates in the running shoes, and just at the year where they started to use them, we see this big increase in endurance. What about the time to exhaustion that we got from the running world records? It's between around 5 minutes. And this is actually something that has been measured many, many times in the laboratory. And this is from a recent review article that summarizes various studies, and the average is slightly less than 6 minutes. This would be the red curve here. We observe slightly lower times, but this might be due to the fact that in the lab, of course, the motivation is not the same as trying to run a world record. And so the actual power output might be a little higher in real world, and that's why the time over which it can be maintained might be slightly lower. Okay, so this is what we can do, or how our model relates to running world records. And now in the second part of my talk, the last 15 minutes, I would like to come to the big data that were collected by running watches, and this is a project we did together with the company Polar in Finland. They provided the data that we analyzed. So what did we do? We had information on distance and time for each run that the runners did. We had about 19,000 runners that we followed. They completed about 38,000 marathons and recorded about 2.5 million running activities. So this was a data set that we analyzed. And we made sure that each runner had training history for at least 120 days before they completed a marathon. So this is the marathon race 120 days before. And then during these 120 days, we detected the fastest performances on 3 typical distances, which is 10 kilometers, 5 kilometers, and a half marathon. And from these best performances, we estimated with our model the performance of physiological parameters that I've shown you before. And then we could do 2 things. We could try to estimate their marathon performance from these parameters. And second, we could see how these parameters relate to their mode of training during these 120 days. And now I would like to share the results of this. Okay. So these are the probability distributions for the physiological or performance parameters that we extracted with our model from the data set. This is the distribution of the maximum aerobic speed, and it has an average about 4.5 meters per second, and it has this nice bell-shaped Gaussian form, which is a typical distribution that you would expect here. This is for the maximum aerobic speed. But what about the endurance? The endurance is a completely different probability distribution. The endurance index, and that's a long distance, the aerobic endurance index, it decays actually exponentially. So it becomes exponentially rare to observe an excellent endurance in this set of runs. Most runners have actually intermediate or actually not very good endurance. And then to have high endurance, it's really rare. So this is what we observed in this data set. These are the parameters. And now, of course, you can ask, how do these parameters relate to the marathon time that these runners achieved? And so what this graph here shows is a data point for each completed marathon, and the color coding is encoding, or the colors are encoding the marathon finishing time. Slow is blue, and dark magenta is fast time. And these data points are plotted in the parameter, 2-dimensional parameter space of maximum aerobic speed and the endurance index. And the dashed lines correspond to all possible theoretical combinations of these 2 parameters that would allow you to achieve a certain finishing time in the marathon. And you see, this is a nonlinear curve for the different times. For example, to if you with a maximum aerobic speed of, let's say, 4.5 meters per second, any time above 3 hours would be possible, depending on the endurance. Now, let me give you an example of this. Let's assume a runner wants to complete the marathon in 3 hours. There are various possibilities to do this. If the runner has a very bad endurance, let's say an index of 3, he would need a maximum aerobic speed which corresponds to about 3 minutes per kilometer. But if the runner has excellent endurance index of, let's say, 11, he could finish at the same time with a maximum aerobic speed of only 3 minutes 42 seconds. So that's a huge difference. And it shows that the endurance index is really something important to take into account. And as you can see, the colors nicely follow these theoretical curves. So we can explain the marathon finishing times to a very good accuracy in this 2-parameter model. Now, what can we learn for training from this? As I told you, we have information also for the 120 days of training before the marathon. And now, with this information on training, we can estimate certain parameters that quantify the intensity or volume or combination of it for training, and compare how these physiological parameters change with the training mode. And on this slide, I'm showing you how the endurance changes with the different modes of training. The first graph shows you how the endurance changes with training intensity. And now it's important here, of course, to measure training intensity for each runner individually in terms of their individual maximum aerobic speed. And that's what we have done. So we divided the average training speed by the maximum aerobic speed for each runner. And then we observed, this is the average in the gray zone, is the variance around it. We observed a very nice exponential increase of endurance with the training intensity. So this is so training intensity, this would be 50 to 80% of maximum aerobic speed, and you see there how the endurance increases. Now, there's another interesting parameter that quantifies a combination of training intensity and volume, and it's called trim training impulse. And what you do for a trim, it's basically a quantity that assigns to each, let's say, minute of running, a number of points that are determined by the intensity in an exponential fashion. So let's say easy running would be 1 point, and then hard running would be, or intermediate would be 5, and hard would be 30. So it's a nonlinear scale. This is a known concept, and we estimated these trim points for our runners and compared it to the endurance. And then we observed something, I think, very interesting. So the endurance starts to increase with this training impulse, but then there's a saturation or maybe even a downward trend. And so this suggests that there's an optimum amount of training impulse to reach optimal endurance, and afterwards there might be even some form of overtraining where endurance goes down, or at least it doesn't increase anymore. So this suggests that there's an optimum amount of training impulse to reach a certain or optimal endurance. Now, what can we say about the maximum aerobic speed? And what we found is that it almost linearly increases with the total amount of, with the volume of training. So this is just measured in terms of the distance of running over these 120 days. And so we interpret this as an improvement in running economy, because we don't think that VO2 max has changed a lot. So it's probably the running economy that has improved, and therefore the maximum aerobic speed increases. And this is actually something that you find quite often in the literature, that increased amount of running volume improves running economy, or the energy cost of running. And the last graph, it's a little bit confusing. It took us some time to understand what's going on. So this is a maximum aerobic speed again, now as a function of training intensity. And it seems to go down with training intensity. But then we realized that this is probably due to the fact that if you look at the average training speed or intensity, that if you have slow runners, relatively slow runners, they would always train at a very high relative intensity, just because if it would become much slower, it would be not running, but it would be walking already. So this is, it seems to be really the case that this just reflects the, how should I call it, the bandwidth of running speeds that a runner has. An excellent, like world-class runner, he has a huge variety of running speeds that are between walking and maximum speed. But let's say a slow recreational runner has a much lower bandwidth of running speeds. And this is, I think, what this reflects. So then, when we published our results last year, we got a big amount of feedback from running coaches that said, well, something like this we have observed in practice, but it was never really confirmed in data sets. And so one of the responses was actually quite encouraging. It was a comment or an article written by Matt Fitzgerald, who is a running coach in the US, and he summarized our observations by 3 key findings, on which I think agree. It's a nice way of saying it. First one, running more is the best way to run faster. So this is improvement of running economy with volume. Second, there is no such thing as too slow in easy runs. Right? This is the last graph I show you, that if you have a huge bandwidth of running speed, slower running is certainly a valid form of training. And last, training load is not the gift that keeps on giving. And this is our result relating the endurance to the TRIMP, the training impulse, that there's a maximum that is good, and if you go beyond, there is some detraining or overtraining. So, in this last graph, I would like to show you now what the prediction accuracy for the marathon is. Because people ask, we got a lot of questions about our model, how to predict races and times, and what the precision is. So we took race performances up to the half marathon, estimated the parameters of our model, and then used these parameters to estimate the marathon time. And what I'm showing you here in this histogram is actually the error in percent between our estimate and the actual time. And the color coding corresponds to different finishing times. And blue is slow, and then the dark magenta is really fast times, below 3 hours. And what you can see is that the slower runners have a typical error of most of it is like between plus minus 10%, which is rather good if you compare it to the single parameter models that I showed you at the beginning. But what is also interesting, if you look at runners that run marathons below 3 hours, the error is perhaps 1 or 2%. And we think that this has to do with the fact that they run much more consistently on the very different distances, and therefore we get a much better estimate of the model parameters from their previous performances and can make a better estimate. Okay, so I think or hope that I could convince you that, and this was only one example for running, there's much more to do in terms of cycling, rowing and so on, where you can construct similar models, that if you have a big data set, there's actually interesting information encoded in it, and we can learn probably a lot how training changes physiological parameters, how they determine future athletic performance, and so on. And I would like to thank you for your attention, and I would like to come back to the weather conditions that I mentioned at the beginning of context complex systems. Something, of course, that we can never predict is if the race happens in weather conditions, and I like this photo very much. This is a race in Boston in a big thunderstorm in the summer of 2015. And so this affected even the top level runners a lot because of high levels of rain on the street. So this is something you can never predict. Thank you.
C'est mieux? Okay. Thank you, Emig, for this very nice and convincing presentation. Well, sometimes impression. So I now turn to the audience to take some questions. There are 2 people in the room with microphones, so feel free to come forward and call them to ask you a question.
Thanks for this very nice presentation. Do you think your model could be used to detect doping?
Yes, so I would say it can be used to at least identify suspicious cases, as I've shown for the women world records. So these two cases, these two examples, 1500 meters and 3000 meters, clearly deviate more than all other distances from our prediction. And we found this reports in the news that there has been doping in these two cases, yes.
And do you plan to test that in the future for doping detection, or is not a new plan?
Well, the question is, so it's always, okay, so I should say that of course world record performances evolve over time, and at least the last couple of years have shown much more improvement than the years before, probably because of new, as I said, running shoe technology. And so during these years where things change, you might accidentally see a larger error for 1 or 2 years until the other distances adjust. But if you see an error like this big over years and it doesn't adjust, then I would say it's a suspicious case. Well, I mean, if there would be interest, and I mean, we could look at, compare, this is for world records, we can do this of course also for individual runners, and let's say if they have one distance that kind of deviates a lot from their performance on other distances, this would be perhaps also suspicious. But I would never use this model to, let's say, prove, of course, some form of them. So it's just to maybe identify suspicious cases and look at them more carefully.
Thank you. Another question?
Hello, thank you very much for your talk. That was interesting. My question is about your model. Would you be able to use it or derive from it a way to predict like future limit record of the 100-meter run or marathon run?
Okay, so the model is basically a combination of the linear running economy relation and this function that describes endurance. And if we combine these two equations, we can get a relation between time and distance, so we can solve for time. And so mathematically it looks like this. You have an equation that gives you the time as a function of distance, and this function also depends on these parameters that we estimate. So as soon as we know the parameters, we can estimate the running or predict the time for any distance you like. And these parameters we get from the performances that were achieved on other distances, shorter distances.
Yes, thank you for the talk. I was wondering if you could go back to one of the slides where you have VO2 max on the left and endurance on the right. It was in the first part of your talk. I'm not an expert at all in big data, and I was quite surprised by your interpretation.
Which slide do you mean?
Yeah, keep going back. Yeah, this one. Yeah, okay.
Which one?
No,
this?
go forward, move forward. Next one, I think it's next one. Yeah, this one. So your interpretation, if I'm not mistaken, for the endurance is that from the increase year 2000 is due to the appearance of Eastern Africans runners, and then on the top right due to the apparition of the carbon plates. Is that correct? This is your interpretation, right?
Sorry, can you repeat the last top right?
Yeah, keep going. Click again.
This one.
Yes. Okay. So I'm quite surprised because to me the Eastern African, they started to run in 1960, not 2000, and then the carbon plates, they are known to improve energy cost of running, not endurance. So that's why the interpretation, again, I'm not an expert in big data, but the interpretation is quite surprising to me.
Okay, so 2 points. If you look at where they appeared in the big city marathons, it was really, I think, around 2000 that they started to win the big city marathons, the African runners. They have run marathon before, but I think then they become really dominant. That's at least what we found. And the second point, the further improvement in later years, where I said it's probably related to shoe technology, I fully agree with you that it appears surprising because it's believed that it improves running economy or reduces the energy cost of running. So you should see it in an increase in the maximum aerobic speed. But this we don't see. So we found it surprising, but on the other hand, you can think of these running shoes also improving endurance in the sense that they maybe reduce the drift in the oxygen uptake over time that is responsible for this logarithmic scaling. So it might reduce muscle fatigue. We really don't know what it does, but our interpretation is based on this because it's really this sharp increase in endurance after the introduction of these shoes. If you have any other idea what it could be, and also if you just, without any model, look at the world records of the last years, they have been multiple times broken on the longer distances since the introduction of these shoes. So I think maybe it's not really fully understood what effects on various physiological aspects these shoes have. I agree with you that the lab tests show reduction in energy cost of running, but that's maybe not all of it.
Last short question.
Thanks for your presentation. I have more general questions about the model, but just I'm coming from machine learning area and working on sports performance. I want to ask you if, for you, trying to, what can you consider as team sports performance?
So what can I consider as what?
What would you consider as team performance? Because here you are focused on running, and it's easy to know what is the performance. But can you generalize something for team instead of individual play?
So what kind of, can you be more precise? What kind of team sports you have in mind?
Soccer.
Okay. Well, so this is a model that is supposed to describe endurance. So this is not a model that would kind of, let's say, describe interaction between athletes. So if it comes to soccer, we could estimate for each soccer player their endurance, perhaps, for running. But it's not a model that would kind of model interaction between athletes or describe team sports. That's not what it is.
No, I understand. Not just a question for you and with your opinion expert. Just if you can tell if for you can consider informed team performance instead of win or lose. For example, with the resistance or anything else, but is it possible with team? But just about the opinion, not about the model.
Maybe so. Okay, so maybe can you give an example? What activity would be you're interested in for your team?
Quantifying something draw with training. Athletic performance, we have many athletic performances, like running. Mm-hmm. But in the literature, there is no really one measure that represents team performance. That's why I asked you if for you there is any measure that can quantify team performance?
I must say I really haven't really thought about what could be specific to teams. I guess
if you tell me no, it's
something
an answer for me. If you tell me no.
Okay, Ryan,
I think we can.
you can carry the discussion after the session. Okay, I am afraid it's time to close the presentation now. Thank you to the audience for your presence and your questions, and thank you again, Emig, for your performance. And I propose that we give him a final round of applause.